Hello and welcome to today's ChemAxon webcast, ChemInfo Stories. My name is Jan Christoffersen and I'm an application scientist at ChemAxon, and I'll be hosting today's virtual event. Today, two of my colleagues will walk you through the topic of substructure searching on the Enamine REAL database using JChem Microservices. With that, I'd like to welcome Wolfi to our virtual stage. Andras Wolford obtained his PhD in physics, studying nonlinear dynamic systems and chemistry from the Budapest University of Technology and Economics. He also holds an MSc in pharmaceutical engineering. He has over 20 years of demonstrated experience in chemoinformatics, including structure representation, stereochemistry, molecule searching, and various database technologies. He's the co-owner of ChemAxon and is now product owner of the JChem search engines. Wolfi, over to you.
Hi, I would like to speak about JChem Microservices and how we use JChem Microservices DB module to search on Enamine REAL dataset. JChem Microservices is a set of tools for chemistry handling, a chemical toolkit. This toolkit is a modular. It contains specific modules for specific functionalities. These functionalities grouped into the modules, and these modules are working together. They're like Lego bricks. This is a scalable toolkit. So based on your needs, you can scale up and down your services, whether you are running on a peak time when multiple hundreds of users would like to access specific functionality, or during the night, you can scale down the service if there is nobody is using a request for an endpoint. It is easily manageable because it contains a central configuration service, which is providing configuration for all the modules. And it is cloud-agnostic, which means that it is indifferent whether you are running this service on an AWS cloud or Azure or Google Cloud. It runs nicely. What microservices are good for? So since it's a toolkit, this toolkit can help you to assist your drug discovery and provide a single piece of truth for chemistry operation and a consistent backend for all your software which is using this service. On the other hand, it is also extending the functionality of your idea with chemistry. So we are going to use this tool, the DB module, with our idea to provide Enamine REAL chemistry search for other software usages. Let's speak about the ChemAxon specific modules, which is providing the chemical functionality. First, we have a structure manipulation module, which is responsible for stereo, chemical calculations, auto mapping. You can use it for standardization of your structure or generate 2D coordinates of your structures. There is the IO module, which is providing the format conversion, mostly use mice and MOFI conversion. That's the typical use case, but also can generate images for chemical structures. The calculations is providing the property calculations like log D, log P calculations for your chemical structures. Also can calculate tautomeric forms of your structures or hydrogen bond donor and acceptors. And provide functionality for chemical terms where you can do isomer enumeration, conformal selection, or topological function calculations. The DB module, which we are going to focus on later, chemistry search engine and chemical storage. We have the Marcus module where we can provide Marcus enumeration, and reactor module where you provide a chemical reaction and reactants, and then you can enumerate your chemical space. And we have a structure checker functionality, which is working like a a chemical spell checker. So it is used typically in an interactive use case when somebody's drawing your chemical structures, and such like a chemical spell checker, it is highlighting you if you are not following the business rules provided by your company. I would like to demo you a very simple auto mapping calculation and show you how these modules are working together. So I go to the demo page and I would like to calculate the auto mapping of the chemical structures. So I go to the structure manipulation tool, I go to the auto mapper functionality, and oops, here, yeah. And we'll calculate the auto mapping for this chemical reaction. If I execute this one, this is the reaction, I get the mapped reaction, which I would like to visualize. So I have the mapped reaction, and to be able to visualize that one, I take the output of the endpoint and convert it to JSON. I go to the next endpoint, which is the JSON converter. I'll provide the calculated string. Take the output of the converted string. And visualize it using the IO system. With the batch conversion, oops, not but with the batch conversion, but with the binary conversion, I will take the structure, which I just converted to a JSON format. And I don't provide the input, not smice, but on the output, I will generate a PNG image. And I will want to see the atom maps. If I execute this one, I get a generated image, which is unfortunately very small. So let's generate a little bit bigger image, which has width 720 pixel. And then I can see that my chemical reaction is auto-mapped. Here, I used 3 endpoints. One was just calculating the mapping. So that was a specific functionality just for the mapping. And then I use another function, which was generating the JSON, and then the image generation. So this is how these small endpoints, very specific endpoints, can work together to generate a mapped reaction and visualize it. Okay, let's go on and speak about a little bit the non-ChemAxon specific modules. So these modules are not providing any functionality related to chemistry, but it's providing the framework for the microservice environment. It has a gateway module, so that's where you access all the microservice environment. Your REST call is coming to the gateway, and this gateway is routing the request to the specific module. And it is also supporting predicates and filters. So if you want to provide a user authorization, that's the point where you can provide it. Discovery module, it is where the instances, the modules can register themselves, and then this registered instance can discover each other's. Finally, a config server, where we provide the central configuration for all the modules, for the chemistry-specific modules, and this can be provided as a resource-based manner. This setup is called the microservice system mode setup, where you have these non-specific non-chemistry specific modules, non-ChemAxon specific modules. And this setup can provide you highly available setup. This can provide you the scale up and scale down, the scaling. But you can use all these modules, or let's say the chemical intelligence module, in a standalone way. And that's what we are going to use in the DB modules when we use it for the Enamine REAL. In this case, no gateway, no discovery, no config server will be used, and not even further modules, just the database module. So what is database module is good for? It can store and search chemical structures and reactions and some additional data joined to this or added to these chemical structures, and execute chemical search, duplicate, full fragment, substructure, and similarity search on this data set. It can use all the chemical features, the chemical query features on the query structure, which you can broaden the search results or narrow the search results. This DB module has a very nice feature, which we call hit as you draw feature. And as the name predicates, it is providing you an interactive behavior. For this interactive behavior, we need two features. First, that we don't return all the hits, but we return the first, let's say 100 hits, but very quickly. This is the interactive behavior. When you want to see the hits, you don't want to digest multiple hundreds of thousands of hits, just let's say the few 10 or 20 hits. The other, which is needed for the interactive behavior, that these hits are not in arbitrary order, but the hits are returning according to the relevance to the query structure. We can say to the similarity of the query structure. So that's how the query structure are defining the hits and also the order. Probably it's easier for me to demo this hit as you draw feature. So I will demo it for you on the Postgres demo page, but this feature is available not just on the Postgres cartridge, but also in the microservice. We will use the Campbell 21 dataset with 1.6 million structure, and we will execute substructure search. So when I start drawing my structure, you can see that instantly I get back the first, in this case, 5 hit, and the most similar structure appears on the first page. And if I'm drawing my structures, I get this interactive behavior. We will use this interactive feature, this nice hit as you draw feature, later on in the Enamine REAL dataset, because there we have multiple hundreds of target structures. So I would like to follow up on the first try we did with the Enamine REAL. That was in 2019, and we were following a monolith setup. This means that we used one JChem Microservice DB instance to store 720 million of structure for substructure and similarity search. That was our goal with an interactive behavior. So we used the DB service, and we needed to configure the DB service. And for the configuration, we went to the memory requirement. And we can see that if I'm following the cache and memory calculator for the microservice DB instance, and I put here 720 million of structures, then I can see that I need 390 gigabytes of RAM. That's a lot. So to be able to handle such huge data set, we introduced the low memory setup usage, when we don't cache all the data into the memory, but we just cache the fingerprints. This operation provides fast, limited search. But if we are going to full type of search. When we want to retrieve all the data, like in a case of benzene ring, we want to retrieve, I don't know, 790 millions of structures, then it will take a lot of time. But as I mentioned, we are focusing this interactive behavior. And also, we are not caching information related to update operations because this is a static data set. We don't need to update it regularly. With these settings, we can reduce our memory requirement to 7 gigabytes of RAM, and that's what we have calculated here. And for this memory, we used an EC2 instance with 16 virtual CPU and 128 gigabytes of RAM. The next step is to convert the smice to JSON. The smice was 19 gigabytes in a zip file, unzipping it and cutting into 1 million of chunks, so 1 million structure in each chunks. We ended up 90 gigabytes of storage needed, and to import and index this 720 1 million chunks, it took 3 days and 9 hours. To start the setting service, it took 5 minutes to load this 70 gigabytes of fingerprints into the cache. And let's go to the query structures which we tested this system with. With the query structure, we used well-defined structures, which are drug-like structures with multiple chemical ring systems, or we used the adamantium cage ring system. We used some scaffold ring systems. We used very generic query, which is this one, where we have just 2 double bonds, and these double bonds are connected to one single bond, but one double bond is a very specific one, which should be in trans. On the other hand, this seems to be very generic query. Then we also went with other ring systems, alkane chains here and there, 1 double bonds. Another ring system is very specific in the stereochemistry, or another ring which contains list atoms here, when we can have carbon, nitrogen, oxygen, or sulfur in the ring, or other ring system where we have link atoms, not link atoms, but atom list. And also we have link atoms here where we have in the query. So we can see that even we use queries features here and there, even bond query features and specific and very generic ring and query atoms and bonds. Taking these queries and executing the search, limiting our search to 100 hits, we get back the search times. This figure is showing the queries on the x-axis, the execution which took to get back the first 100 hit on the left x-axis, left y-axis, and the hit count on the on the right side of the y-axis. We have queries where we don't even get 100 hits. We have queries where we have 100 hits, and we see the execution time, but it is quite distorted because the slowest execution times are dominating the picture. So we see that 2 queries are running quite long. It took more than 100 seconds. But if we want to see an overview of the search execution times, then we can use this other figure when we see that how many seconds took to finish a given percentage of the 52 queries. And we can see that 60% of the queries, so from the 52 queries, 60% is finished just under a few hundred milliseconds. And in 3.5 seconds, we finished 90% of the queries, and that's 2 queries remained left, which took long time to execute. And let's see that what could be this 2 query. Why did it take so long to execute the query? And we can see that these are generic queries. So we have list atoms here in the ring and list atoms on the ligand, and which makes it very slow to execute is that this list atom in the query can generate an aromatic ring in case of nitrogen and an aliphatic ring in case of carbon. Okay, let's see that how do we see if we are going with higher limit with 1000. Then we see that other query which was very fast in the previous example took long time, and this query again a very specific one, sorry, a very generic one, which is this trans double bond. If we check the overall execution time, we can also see a similar picture what we've seen previously, that in 2 seconds, 80% of the query is executed, and just 5 queries remained, which took longer than 2 seconds. Okay, if we are going to similarity search, then that one is executed in much faster. Again, we are limiting our search with the first 100 hits and with a similarity threshold 0.8. And we can see that similarity search in the slowest way took 3.5 seconds. So it's executed very quickly. And if we take the overall view, that what are the overall view for the similarity search, and we can see that under a second, 90% of the similarity search is finished. If we go and take another setup, when we are searching for the Enamine REAL search, but not in a monolithic setup where we store everything in one instance, but instead we store shards, or we cut this, the database into different pieces, different shards, and each shard is responsible just for the search on the specific shards. And then we create a service which is merging this, these results from the specific shards, then we can even speed up the search. So merging the results with one service and using multiple services to execute the search with this distributed setup, this is going to be evaluated and discussed by Strats András. And with this one, I will finish here. Thank you for your interest, and provide the stage for András Strats, who will speak about that how can one use this distributed setup to find analogs in the Enamine REAL space. Thank you very much.
Thank you, Wolfi. Next up is András Strats. András is a computer scientist who joined ChemAxon in 2009. Since then, he has been working on advancing ChemAxon's web-based products, such as Chemicalize. In the last few years, he has been the product manager of Design Hub, formerly known as Marvin Live. András, the virtual stage is yours.
Hey everybody. So in this video segment, I describe how you can use Enamine REAL to find leads and analogs, and somehow connect this story to JChem Microservices. Let's start at the problem, which is that during any compound design and iteration process, to prioritize the ideas, it's essential to have access to purchasable compounds. And typically these were done using large aggregate catalogs like eMolecules, MQ, Moport, Namiki-Shoji, and the like. But the virtual catalogs really take this to another level nowadays. And there's a handful of them even available. One of the most prominent ones, of course, is Enamine REAL. It's been around for 5 or 6 years, and it's been growing steadily since its introduction. Nowadays, it's available in kind of two forms. One has 2 billion compounds and the other has about 15 billion compounds. So now we are reducing its size to 10 to the power of 10. But there are other kind of close followers as well, like Wuxi Galaxy in one form is available at around the billion compound mark. And many pharma companies are also launching their similar size proprietary spaces. So to keep up with these options and the growth of these data sets, and to take advantage and exploit the possibilities in these chemical spaces, you need a scalable platform. And that's what JChem Microservices offers. The search engine within that, JChem, of course, also offers all the typical search methods like substructure, similarity, exact search, full fragment search. And they also offer lots of query fine-tuning options for stereo handling and the like. So next question needs to be, which ones do we pick and how do they work on this Enamine REAL? So using a Pfizer paper on a kinase inhibitor, I looked at how does the search engine behave and what sort of results do we get. On the left, you can see a reference compound. This was used as a query. This is a drug from the paper, the kinase inhibitor. And on the right, you can see the most similar hits retrieved. And although there's about 300,000 similar compounds available with a reasonable similarity cutoff of 0.7 tenimoto, the most similar compound is not that similar, not that useful to us. So we need to make some changes. If we remove the decorations, which I have done from this bottom-most ring, then we can see something interesting. So first of all, the most similar compound is starting to point in the direction that there might be something useful in the data set. And the similarity scores reflect this. So it's now 0.89, 88. But also, seemingly the available chemical space to us has grown 4 times. So let's do one more iteration and see where that takes us. So if we cut down our query structure to just the essential part of the scaffold, then the most similar compounds are really interesting and really useful to us. And again, we have increased the chemical space available to us twofold. So we have gone from about 300,000 to 2 million by capturing what's the essential part of the query. This is going to be a key point. But let's also look at substructure search. So the way these data sets are created are using many tens of thousands, but certainly not millions of building blocks, and some reaction equations or synthesis schemes that are applied to them using a reaction enumeration engine. So a substructure is either going to not hit anything, or it's going to hit a lot of the compounds that share those building blocks in some way. In this case, for this core fragment, we actually do get about 17,000 compounds, but the results pose a challenge. In that substructure searches are typically not ordered. So we need some ordering mechanism. The nicest method probably is ordering compounds by molecular weight. And JChem actually offers a close default. Results are ordered by similarity to the query. And so if you apply that sorting and now look at the most similar 4 compounds, then the results become really interesting and really useful to us. So this is a second key finding, that substructure searches should be ordered somehow by size. In the context of JChem, this also has a massive benefit with respect to improving search performance, but more on that a bit later. So putting this together, the decoration-free query structures and similarity search seem to capture really large pools of options in Enamine REAL. And some substructures also match large sets of compounds, of course. On both of these cases, ordered retrieval is going to be very beneficial, but most importantly, fast retrieval is going to be essential. Otherwise, we cannot effectively prioritize our compounds. We cannot tell in these large spaces which ones have available purchasable compounds and which ones do not. So how fast? How fast can we make this? Here's a kind of a short video. So we just set the reference compound that you have seen earlier, and very soon after our physical chemical properties appeared, so did our most similar 20 search targets from Enamine REAL. So that's the performance that we're able to hit. So one more time, if we set the reference, then in about 3 seconds, you get your similarity hits. This is not just one case. So I looked at about 50 benchmarking compounds from 2 chemical projects. One is IREC4 and the other is the Pfizer paper on pangenous kinase inhibitors. The substructure searches, of course, were ordered by similarity to the query. Similarity searches had a cutoff of 0.7. And then we look at different number of hits requested from the search engine. And here's kind of this small spreadsheet on how the performance looks like. So with both substructure and similarity search, we can hit about 3.5 seconds when we request 200 most similar hits, and we are getting 4.3 seconds at around 20,000 most similar compounds from the search engines. So it shows that it scales remarkably nicely with the logarithm of the search hits. So the correlation, the relationship is between the number of seconds with the log of the hits. We are really happy with this. And so the way we apply this in our application design hub in kind of this end-to-end solution, this is in the IREC4 project. So we have about 150 compound ideas in this bicyclic series. And we want to see which ones can be taken further and which ones cannot. So this is the prioritization challenge here. We already have a bunch of properties calculated for these compounds, but let's add enamine. Let's see how that helps us. So how can we do that? So we hit add properties, and then from the drop-down, we just select enamine and pick which search type we want, either similarity or substructure. Really, really simple. And then in a couple of seconds, we get our similarity scores and the best hits ID on our cards or in our spreadsheet, depending on how you want to look at it. And so I also applied a filter. So I only want to see compounds that have a highest similarity larger than 0.8. And so from what I can see here, about half of the compounds, so about 77 out of 150, have a highly similar analog available in Enamine REAL, and the other half doesn't. So that's one of my first key prioritization achievements. I was able to cut the data set into 2 halves. The little bar chart also shows that the first four or five compounds have something very, very similar in the set, and then there is another cluster. So we can further fine-tune this, but we can also drill into one of the compounds if that proves to be a tricky case. So I just click on the compound, then it's loaded into the editor, and then on the right I get more details from each of the tools that we can use to characterize this compound. Enamine shows its most similar compounds, but I also get a peek into the medicinal chemistry properties of the compound. And I can also assess some of the liabilities that I might have with the compound, like assay interference or freedom to operate type queries. And then I can refine the compound, perhaps come up with another alternative, and in just a couple of seconds, I get my updated search results for that. So it actually couldn't be simpler. And then one more peek into what we built and how we built that. So underneath this plugin result or this window, we have the scalable infrastructure with some sort of an API. So of course, that's what we plugged into the end-to-end solution. So how does that work? So this is just for the kind of the technical geeks out there who might be interested. So the first step is that we request some configuration from our authentication pool on Amazon. This is a Cognito pool. So we request the token endpoint. And then using the token endpoint, we log in using our credentials to obtain more or less a temporary access token. And then with the access token, we can simply fire our searches. The searches use this JSON formatting. They include our authorization token, and they also include the query molecule, which we may have, the search type, which would be then similarity or substructure, a similarity threshold, if we want to set that, the number of hits we want to receive, or perhaps a timeout to the search duration for an interactive use, if you want to specify that. And then in just a couple of seconds, we get our search results. So these two actually couldn't be simpler. We get our Enamine REAL IDs, our hit molecules, and then their similarity scores. That's pretty much it. This is what we used to create the screens that you have seen earlier on. So that's Enamine REAL and Design Hub in a nutshell. But Design Hub also offers a few more things. I thought you might be interested in that. With that, you can do the whole end-to-end design process in one single application, starting from capturing your hypotheses or scientific rationale and questions. Then you can follow that up to compound design and the prioritization that you have seen as well. And then very importantly, you can continue tracking the synthesis of the compounds with your CROs. So the whole deal of designing and prioritizing and tracking compounds is available in Design Hub. If you're interested, please just get in contact. Thank you.
Thanks, Andras, and thanks to you, the audience, for attending. We hope to see you on our upcoming webcasts and also at our online community on LinkedIn. There we have the ChemAxon Users Group, a closed group for verified users to engage in quality conversations, whether that be asking questions, sharing your opinion, or connecting with speakers and peers. To recap, you'll need to search for the ChemAxon Users Group on LinkedIn. We look forward to seeing you soon. Stay safe and goodbye for now.